Hello! As you can see, we're on everybody's favourite graphical calculator, Desmos, desmos.com/calculator if you want to draw along, and we're looking at transformations of graphs. But also, before we get into that, I need to just go through the three trigonometric graphs. If you haven't seen them, then here they are. So you've got sine, cos, and tan on your calculator, and if you plot out all the values for sine x against degrees along the bottom, then we get this oscillating curve, sinusoidal curve. The sine wave came first, I believe, and then things that look like this are called sinusoidal after a sine wave. And the key things about it is that you get key points every 90 degrees. So 0, 0, and then at 90 degrees you get the maximum, which is 1, and then back to 0 at 180, another 90 degrees, you're at the minimum, -1, another 90 at 360. And then this repeating pattern, or this pattern, sorry, from 0 to 360 repeats afterwards, and indeed beforehand and forever, both ways to infinity. You get this wave up and down between 1 and -1 and crossing 0 every 180 degrees. I'm not sure there's much else to say about it at this point. You just have to know that that is the shape of the sine wave. So the cosine wave, or the cos graph, looks very similar. It's just shifted along by 90 degrees, like you've picked it up and dragged it to the left. So here's the cos graph on top, so cos is in blue, and you can see it looks absolutely identical. It's just shifted by 90 degrees. So this time 0 starts at the maximum 1, we go through 0 at 90, and then -1, etc., etc., etc. Again, infinite wave, sinusoidal, exactly the same, but just shifted. If you think that's odd that they look exactly the same but shifted, then you shouldn't find that odd. It's kind of built into how sine and cos work. So here's a very badly drawn right angle triangle, and here's angle theta. Now what we know, if it's a right angle triangle, and it's in normal Euclidean space of course, is that this angle up here has to be 90 minus theta. Let's draw that theta slightly better. So these two angles are related. Whatever this one is 90 minus that angle. And if we think about what sine theta is, sine theta is the opposite over the hypotenuse. And if we think what cos of 90 minus theta is, okay, so cos of bracket 90 minus theta, so this is where it gets a little bit crazy. If we're saying cos of this angle, this is the interesting angle now rather than the theta, and so for cos it's adjacent over hypotenuse. So now suddenly, because we changed angle, this is the adjacent side, but we just said this was the opposite. So in terms of, let's not call it O, let's call it, I don't know, O1 or something like that, just so we don't get confused. Yes, this is now the adjacent, and this is the opposite for this angle, but we're going to refer to it as the same as O1. So the adjacent is now O1 over hypotenuse, and that's exactly what we just had. So sine theta equals cos of 90 minus theta. And what we'll see later is that that subtraction is what is shifting the graph. I mean, it's a little bit more complicated because actually what you're doing is you're adding something and then you're reflecting it. But we'll come back to that later on. If I forget to come back to it, we'll go through how it works, and then you can work out how to transform the sine theta graph into that, and it results in what appears to be a transformation like this. Okay, so that's two of the graphs, sine and cos. Tan theta looks a little different. It's the strange one, and here it is in green. And so what you can see, the interesting points, we start at 0, 0, it goes pretty sharply up, and although it's quite far away from 90 there, it is getting closer and closer and closer and closer and closer to 90. It asymptotes. It will get infinitely close to 90, but never get there. So if you did on a calculator, in fact, let's get a calculator up. If we do tan of 89.99999, we get a very, very large number. Add a couple more nines on there, and we get an even larger number. But if you actually try and do tan of 90, it's going to give you an error. It's not going to work it out because it's impossible to have a value for 90. You cannot be anywhere on that line. You can get infinitely close, and then it shoots down, and then a tiny bit over, it comes back from negative. So tan of 90, maths error, can't have that, but a tiny bit more than 90, and suddenly we're in the very big negative numbers, zooming in from the bottom there. And again, these key points change every 90. So 0, and then an asymptote at 90, 0 on 80, and then an asymptote, and then 0, and then and so on and so forth. And that happens in both directions again. So those are the three trigonometric graphs, and you need to know what they look like, and you need to be able to sketch them. And then what you'll need to be able to do as well as that is be able to transform them, and possibly other graphs as well. You may have to transform a quadratic or a cubic or an exponential or whatever, or just transform one point on the graph into a new coordinate. But in order to look at this, we need to look at how the transformations work. So let's get rid of the cos and the tan and just go back to the sine. There's three transformations we can do, and they're similar to the transformations that you do in geometry, your reflection, rotation, translation, and enlargement. Unfortunately, you can't do rotation. There's no way to spin the graph round, not on an XY graph anyway. And so we can't do rotation, but we can do translation. So let's start with that. Translation. And in translation, it is exactly as it is in geometry, where you just like shift it up and down and left and right. And the way it works is this, that if you have some function of x, so y equals some function of x, now in this case we've got y equals sine x. If you add a number after the function, then it's going to shift it up or down. If you've got, so I'm just going to say plus a for now. Whereas if you add the value inside the function, so if you add the value to x first, then it's going to shift it left and right. Okay, let's look at this one first. So adding a number to the function after you've done the function. So in our case, our function is sine x. So pop that in. And if that value is positive, so I'm just going to make a slider on Desmos. So if we've got 0, then, oh no, maybe not. There's 0. If I add a positive amount, so 2, then it shifts the whole graph up. It just literally pushes it up. Whatever the answer is, just add 2. So it increases the y value by 2, because that's it. You just work out the value, add 2, it's just going to increase the y value. And if we have a negative number, then it shifts the graph down. So here's minus 0.8, and of course it goes through the axis at minus 0.8. Just like on a linear graph, y equals mx plus c, the plus c is just where it starts on the y-axis. It's exactly the same thing. The plus at the end will tell you where it goes through the y-axis. Can't do anything about it. That's what it's going to be. Easy peasy. The x-axis, not so easy. So let's get rid of that. Back to normal, but this time what I'm going to do is I'm going to add the amount inside the x. So this time, instead of doing sine of x then adding a number, I'm going to do x plus the number and then sine of x. And the way this looks in the function notation is to say, y equals f of x plus a. So adding it inside the function instead of outside the function. Well, what's that going to do? Now, you might think, oh, well, it's going to be the same thing. We're adding something. It's going to shift it, that amount, a, and it's going to shift it to the right. Unfortunately, that's where you're wrong. If I make the a value 3, you can't see because, or you might be able to just see it's moved slightly, but of course I've just realized my axis is in 90s, so I just need to amend Desmos slightly. So if we go to there and there, right, so now when I adjust my slider, if I add 90 or 135, it's actually moved to the left instead of to the right. And this is counterintuitive. You'd think it would move to the right, and it doesn't. Of course, if I take away, if I make the a value minus 90, then it has shifted it to the right. So what's going on? Why is it going seemingly the wrong way? Well, of course, it isn't going the wrong way. We have to think about it carefully first. So if you want to know the sine of 45, so here's 45, and I work out the value. I should have picked some nicer number, shouldn't I? But there we are, whatever that number is, 0.6, almost 0.7, so 0.68 or something like that. I could work it out on the calculator, but it doesn't matter what the value is. I work out that's the value at sine 45. And then I say, oh, actually, can you do sine of 45 plus, and the amount that I've added on just happens to also be 45. So I say, okay, well, here I am at 45. I add 45, which gives me 90, and that would give me this coordinate here. That's the value I work out for y, but I'm going to plot it where I am, and I'm at 45. So you get the point there. And when I'm at 90, and I say, okay, well, 90 plus 45 is going to be this value here, but I'm still stood at 90. I'm stood at 90 asking for the amount of y when I would be stood 45 in the future. So it's like you're stood here saying, in the future, what would the value be? And plot it here. And here you'd say, what's the value in the future? And plot it here. And so you're looking, it's like you're stood here looking into the future and plotting that future value. So you get a shift from the future to the left to where you are. And that's why it is going the wrong way. If that doesn't make a lot of sense to you, don't worry about it hugely. You just have to remember that when you are doing something that affects the x-axis, it's counterintuitive. And you'll see that in the enlargement / stretching in a moment. Right, so that is the translation. Adding inside moves it to the left. Adding outside the function moves it up. What else can we do? Well, the next one I'm going to look at is sort of like enlargement, but it's not. So I'm going to call it a stretch instead. Okay, so an enlargement, if I've got a box, I'd enlarge that a bit bigger that way and a bit bigger the other way. I have to make every direction bigger at the same time. And I can't do that on the graph. I can only do it one axis or one direction at a time. So that's why I'm calling it a stretch. I'm only doing it in one direction at a time. And it's the same thing. If I have y is a function of x and I multiply the whole function by an amount, so a, for example, then it's going to stretch it in the y-axis. It's going to make it taller and shorter. Well, if I times it by a positive amount, it'll make it taller. And if I times it by a fractional amount, then it's going to make it shorter. Whereas if I do the function of x, function of x, but I multiply that x by a inside the function. So if I times it x first and then do my sign, then it's going to have the effect in the x-axis and make it wider or thinner or squashed left to right instead, just like before, outside the function, up and down, inside the function, left and right. But again, it's counterintuitive. So let's have a look at putting h on, not h, sorry, a outside the function. Just give me a moment to do that. So if I have it outside the function and I make it big, then it gets bigger, it stretches it up. Notice that the points on the x-axis stay exactly where they are. They're like anchor points. Okay, it's only everything there stays pinned. It's everything else that stretches up above the axis and stretches down below. Okay, so make the number bigger and it all stretches, and it's just stretching up and down. If I make that number back to 1, then you get the original. If I make it a decimal, then it squashes it flatter. Okay, we'll come back to what happens with negative in a bit. So let's put it back to 1. Now what if I move that now, so instead of timesing outside the function, I times it inside the function. If I make it bigger, then it actually squishes it in. So again, it's going the opposite way than you would expect, or on first glance perhaps. Maybe you've realized that that's what's going to happen because of what happened with the translation. So the bigger I make it, the more squashed it is, and if I make it a decimal, then, if I make it a decimal, there's 1, and make it a decimal, then it stretches it out. Again, why does it go seemingly the wrong way? It's exactly the same reason. If I'm here at 45 and I say, we'll work out what the value is, 4 times further away, here I am at 45, times it by 4 first, 180, and it brings the future back, so it brings that 0 point. So now it's got to go up and down in a much tighter range rather than having the whole, all 180. So it's just this idea of here you're working it out and then stretching it afterwards. Here you're saying, well, what would it be if I was that number, and then plotting it where I actually am. The last one to talk about is reflection. So, sorry about my terrible handwriting on that. If you want to reflect, you use a negative sign. So for this, I'm actually going to change to using an exponential graph instead. So here's a lovely exponential graph. We'll get rid of sign. And the reason why I'm using an exponential is because if I use sign, then one axis, you won't notice the difference. When I reflect it one way or reflect it the other, both reflections will look identical. Whereas here it will be clear which way it's reflected. So there's two options. We can again either do y equals and do minus the function of x. We can have the negative sign after we've worked out the value, just shove a minus on right at the end, or we can have y equals and we can have the function of minus x. So which way will do which reflection? Well, if you think about it, if you work out what the value is, what the y value is, and then minus it at the end, you're making the final y value, if it's 2, you're then just going to plot it at minus 2. So putting a minus in front of the whole function is going to reflect it in the x-axis. And we can show that if I just put a minus in front of the whole thing, it reflects it in the x-axis and back. Whereas if I put a minus just in front of the x, sorry if you didn't know what the equation of this one is, it's y equals a number, in this case it's 1.01, but that's just because I've got a crazy scale going on, to the power of x. So for this one, I just put a minus in front of the a, whereas this one, I'm putting a minus just in front of the x. So make it negative first, and then do the maths that you've got in your equation. And in this case, it will flip it in the y-axis instead, just like that. Those are the 3 transformations of graphs that you can do. The stretch, the translation, and the reflection. And you just have to remember what the 3 different ways of doing each one is. And then if you've got a complicated one where it's happening, you've got lots of different things happening at once, then you can you just do them in the right order, and the right order is the BIDMAS order that you would do a calculation. Right, let's just have a quick look at two little examples. So here's my sine graph again. Actually, just before we do an example of the transformations of graphs, there's one thing I forgot to mention about the sine, cos, and tan graphs, which is that there are lots of x values, angles, that will give the same y value, which is obvious when I say it, but you have to have it pointed out that we're used to, in our calculator, having the 0 to 90 values given to us. So if we ask the calculator what is, shift tan of whatever value, and it gives us an angle here, but that's not necessarily well, it isn't the only value that would work. And if I just leave sine up, then I can show that because, or not because, but I can show that by saying, okay, if sine of 50 is 0.766, well, let's draw on where 0.766 is, and it's this value going across. And absolutely, it is, well, okay, it says 49.996 because I rounded it, I truncated 0.766. But you can see it, assuming that was absolutely right, then this straight line intersects the graph at lots of places, and of course off the screen as well. So we can see 5 values, 5 angles, 2 negatives and 3 positives, but there's an infinite number because this graph goes on forever in both directions. So you may find a situation where you're asked this, find another value of x for which sine x equals 0.766. And the trick is that you use these, well, that's a stationary point, but these key points where this 0, 0, and this one's at 0, and that's at 0, or you use the maximum, or you use the minimum. And you say, well, okay, sine 50, well, that's 50 more than a 0 point here. So it's also going to be 50 less than this 0 point because it's symmetrical. So whatever 108, well, that is 180, and whatever 180 minus 50 is, should be the coordinate there. So that should be at, what I say, minus 50, so 130, and okay, 130.004, but that's the rounding, the truncation error. So you can use the symmetry to work out lots of values. And because it repeats every 360, if 50 is an answer, then you should be able to just add a 360 to that. 360 plus 50 is 410, and there it is, 409.996 should be 410, and the next value will be 130 plus 360, and it's very predictable what these values are. Okay, well, let's take that away and have a look at the transformations. Very easy question here, and then a difficult question, and then I'll leave it with you. Find the maximum of 2 plus sine x. Well, you don't need to draw a picture of it. You can have a think about this. This is a very straightforward one. You think, okay, well, what is the maximum of sine x? Well, we know that sine x and cos x, they oscillate between 1 and minus 1. So the maximum value is 1. But then if I'm going to add 2 to that, then it's going to increase it by 2. It's just going to move the whole graph up. So it's actually going to go off my page. It's going to go up to 3, and that's going to be my maximum value is going to be 3. It's going to be 1 plus 2 is 3. And I could try that. I could move a, so it is, oh, I think I got rid of too much stuff there. I could move, I could have got a slider here, so I can change a into plus 2, and you can see it goes shooting up, and now it's going from minus 1 through 2, and off the screen, I promise it is going to 3. So you don't need to draw the graphs, you can just think about how would the graph move, and then all the points will move in the same way. It does help to sketch it in a in an exam, or if you're doing a question, a little sketch can really help. Let's do another one, and here we have you can see quite a complicated question. we've got everything going on here, apart from minus signs actually. We've got 4 sine of 2x plus 2, close the bracket, and then add 3. Well, we've got to do this BIDMAS, is what I said before. So we've got to do inside the bracket first, and we're going to do the 2x first. So the 2x is going to squash it down. So that's not going to affect the maximum values. It's just going to squish it down. Okay, but let's just see what it looks like just to be sure. Yeah, that just squishes it down. The maximum, though, isn't affected. And the plus 2 isn't going to affect it either, because that being inside the function. So I didn't need to think about those at all. If it had asked what's the coordinate of this maximum, where does that maximum go, then I would need to think about it. Plus 2 is going to move it 2 to the left. Now that's not going to, you're not barely going to see that on this because it's such a squash scale. But we can do it anyway just to see there was a slight movement there. So it has moved 2 to the left. Now I've done that, so then we do the sine of that value, fine, and then between the 4 and the 3, of course, we're going to do the 4 first if we're following BIDMAS. And the 4 is going to stretch everything 4 times bigger. So again, this is going to go off the screen. And so make this 4 times bigger, and whoa, right, okay. Now, obviously, I can change the screen, I can zoom out, there we go. So it's going 4 down to minus 4. And finally, the plus 3 is just going to shift everything up in the air by 3. And indeed it does. So now there's our maximum here, and it looks like it's going to be 7. Could I have done that, and there it is 7. Could I have done that without drawing it? Yeah, absolutely. I'd have thought, well, sine is normally got a maximum of 1. These transformations are just changing the x-axis, so ignore them, or process the coordinate if you need to do the x as well. Gets 4 times bigger, so 4 times further away. 1 times 4 is 4, and then add 3, it becomes 7. So you can think it through. Right, I did say I'd leave you to it, but I remember I did say about how do we get sine to cos when we from sine graph to the cos graph, and I said that it was just shifted, and actually it's not. When I drew it, we said, in fact, do I still have this written, or did I? I think I just deleted it off the page. So I said something along the lines of sine theta equaling cos of 90 minus theta. So this isn't just a translation. We've got this plus 90. We've also got a minus on the theta, and this makes it all go a bit strange. If we try and do the BIDMAS like we did before, you'd be tempted to say, okay, minus theta means we're going to have a reflection first. So I'll flip it over. It's on the it's on the x, as it were, the theta in this case, so it's going to flip it left and right. So there you go, a nice flip of left and right. And then adding 90, well, we all know that adding 90 is going to make it move to the left. That's what we said. And yet when I add 90, whoa, it's moving to the right. Well, why has it done that? That makes no sense. We said that adding 90, or adding a number, moves it to the right. Let's just check that if we bring up another graph, so here's the cos graph, and if I put in the bracket plus well, let's say plus 70, well, you can see that has definitely moved to the left, a little bit for 7 and then a lot for 7t. So that's definitely moving to the left. So why is this one moving to the right? It doesn't seem to make any sense. Well, it does make sense if we take each step, if we do one step and then the other before we draw the graph out. So let's have a little look through as one coordinate. If we take this coordinate here, 91, the first thing we're going to do is do minus it. Now, I appreciate, I've just realized I've said that this is the case. Obviously, what I'm doing is I'm plotting sine of 90 minus theta. I'm doing it a bit backwards actually. And if I plot sine of 90 minus theta, I should get the graph of cos theta. So I should have written it the other way around. I apologize if that was confusing you for a moment. So I'm actually looking at this scenario, but it is symmetrical, so that's not a problem. So by transforming my sine graph by doing the 90 and the minus, it should become the cos graph. That's what we're trying to do. Okay, so let's take this point, 90 and 1. If I make it negative, it's going to flip over and it's going to be here. And then you can't just think, oh, and then do the adding. That's what we were thinking before. So don't think, okay, I'm going to flip this point. Think, okay, I'm here. I'm going to plot at 90 the value I get at minus 90, which should be minus 1, but we're not ready yet because we're also going to add 90 to that first. So we're going to say, here is where I'm going to plot this value plus 90, which is actually the 0 value. So here I'm going to plot this value here, and that is going to shift it to there. And you say, okay, well, here I'm going to plot the value at minus it, so it's there, plus 90, which is here, okay, which is that value. I'm going to plot that there. At this value, I'm going to plot minus that value, but plus 90 beforehand, so that's a 0, and you can see that I'm getting the graph coming in like this as the very badly drawn cos graph. For the 0 point, again, minus it is the same, and then plus 90 is at 1. So it's a bit more complicated when there's a negative involved. You can't just go for the bid mass. You have to think carefully about what's happening. If there was a plus in there and then a minus outside, I could definitely take those separately and just be like, oh well, shift it and then do the reflection. But do be careful when you have negatives like this, that it might do something funny. And think, here I am, here's where I'm going to plot it. Follow your instructions to find what the position that's leading you to, and that value, plot it where you are. A little sketch sometimes makes it more clear what is going on. Right, I will actually leave you there. Sorry, a bit of a long video. If you survived to the end, well done. Hope it was helpful. If there's anything you're not sure about, then leave a comment and I will try to address it. Thank you very much, and ta-ra for now.